So we will talk about 3 different sort algorithms. They will perform n log n big O. So earlier you can see, you can compare if you have the n squared sorting algorithm compared with n log n, actually your runtime will be dramatically down. So we show the first n log n sorting, we call the HeapSort. So we introduce this one first. That's because this HeapSort will be in the similar algorithm what you have from our priority queue. Because did you remember your priority queue, your data in the array, they are in the heap order, right? So when we talk about the heap, remember what is a heap structure? The heap actually kind of like a tree. So you only have one parent on the top. So the parent on the top, they will be always greater or equal to the children. Every parent only have at most 2 children, and we don't allow any hole. Right, so that's why here our HeapSort is continue with our priority queue. We try to maintain our array. So since you know that priority queue, that's heap, right? So our HeapSort only work on the array structure. So your array needs to always maintain a heap order like your priority queue. So that means your parent node always greater or equal to the value for the child node. So this one we call the in queue. So then after you maintain the heap order, right? So that's why we know the top node always is the greatest value. So in order to have they are sorted, our sorted we always do the low to high. So that's why after you have all the nodes in the heap structure, we call in queue. Then the second part, we do the dequeue. When we dequeue, that means actually the parent nodes on the top node, they are always be the greatest value. So we will move them into the end of the heap. So that means your greatest order will be in the last node. So after you move so we swap the value for the greatest value and the last node. So then we will have they do one by one, just like the pop operation. So we will maintain the low to high sorted order. So for either your in queue or dequeue, actually do you remember, right? That's the in the heap structure, our level is log n, but we need to apply on all the nodes. So that's why either your in queue or dequeue, their runtime will be big O n log n. So even you have 2 big O n log n, our runtime still is n log n. Okay, so just that idea how the heap sort will work. So the first thing we just see what is in queue, how the in queue will work. So we're in queue like this. We just say, for example, I have an array like this order. We have the number 11, 6, 4, 1, 3, 7, 12, and 8. So definitely this array is not in the sorted order. So when we want to apply for the heap sort, we need to maintain the heap order. So definitely it's not heap order, right? So from here, you may not easy to see. So that's why I show you like this one. So your top node is 11. So you have children. Then the third level is 1, 3, 7, 12. So you have the last node is 8. So we see we don't have hole. So the hole only at the end. So that's why you can see actually 8 is greater than the parents. So they are not in the heap order. So when you have a random array, so the first thing we will do make them become heap order. So that's we mean here. That's we mean the in queue. So we will do the in queue algorithm. So this in queue we will do is you will have make this random array. They will be in the heap order. So on the other hand, you will check one by one, right? So we will see 11. Okay, so then 11, of course, you are top node, so you always correct. So then we go to the next one. So how I know that's heap order or not? So I just need to check if my parents' value greater than me. So then done. So the same thing for, we check your parents' value is greater than me or not. Good, that's done. So then you do the 1. So 6 is greater than me, fine. So 3, 6 is greater than me, fine. So then you will see now if you have any order, you see 7, the value is greater than their parents' order. So the parents' value actually is smaller than the children, so they are not in the heap order. So on the other hand, I need to push up to promote the 7, right? So when you see your 7 is not smaller than your parents, so that's why you need to swap 4 and 7. So after you swap, then 7 is here. So continue, you need to check the parent again. So this parent is greater than 7, so we done. So actually this one, when we call the in queue, that's the algorithm we will do. So you will start for a for loop. So that's why we say you need to have your n. Your for loop index start from 1. Why 1? Because the top node, I don't need to worry. Top node doesn't have parent. So we start from the 6 until the index less than the size. Remember, we use the index. So that's why index less than size, we just continue. So this in-queue structure, in-queue process, actually you work on every node. So in this for loop, each iteration, we will start a loop. I will start a while loop. Why the while loop? The while loop will check, for example, 6, right? I will check if my parent's value is greater than me, then I finish. Or my parent's index is less than 0. So that's why here, when you start the inner while loop, so then here you will have your while loop condition is while your parent index is greater equal to 0. Right? So on the other hand, that's me. When your parent's index less than 0, you exit your loop. So then you know how to calculate your parent's index. Your parent's index always equal to the child index plus 1, then divide by 2 minus 1. So that's our parent index. This one actually using for our while loop condition. So a while loop condition, while the parent's index greater or equal to 0, we do this. So when we find the value at parent index greater or equal to the value of index, actually we done, right? Because they are in the right location. Otherwise, we swap. So after you swap, you make your index equal to the parent index. So you continue with this while loop. So then inside this one is a while loop. Don't you feel this while loop actually equivalent to what? Our push operation. So actually when we originally have a random array content, we want to make them become the heap structure. You just need to go over each value. So each value you will consider to see can they promote to the right location. So on the other hand, you just have a for loop to do each node to do the push operation we did earlier. Right? So that's why here you will see afterward, that's the beginning for the array. So afterward, when you finish this for loop, and inside you have a while loop. So that's the n log n runtime. Then your array at the end will become like this. Right, they are still not sorted, but at least they are in the heap structure. So after your in queue, right, your array will be in the heap structure. So what should we do at the second part? Right, so after they are in the heap structure, now I just need to make them become the low to high order. Good, our sorted array should be low to high, right? So that's why here I know the top always be the greatest one. So when we do the DQ, we always just swap the 12 with the last one. So at least after we swap each one, you see the greatest one will be in the right place. But after we do that, of course, 1 is on the top. So we're missing the top node is the greatest value. So that's why here, the second part, after you have the array in the heap struct, we need to do the DQ. So how to do the DQ? So the DQ, every time you just have your top node swap with the last node. So after you swap, at least we know you see this value in the right location. So then we just need to see, okay, the top node is not in the heap structure. So I need to try to demote or try to find the correct one, come to replace this location, right? So that's why you see you're going down, you're going down, you're going down. So that's why you see here 11 greater than the 1 and 8. So we move the 11 up. So then 1, you are greater than your children 4 and 7. So then we move up 7. So once the 1 at the right location, right, so we have the first iteration finish. We have the last one is the greatest value. And the rest of the nodes, they are in the heap structure. So don't you feel this one is very similar? We see this actually is the pseudocode for you to do. Like earlier we say, you will start from the first node, the top node, always replace with the last one, right? So that's why actually in our for loop, we start from size minus 1. So the index equal to size minus 1, that means the last node, until index greater than 0. So every one index minus minus. So then after you have your last node, right? So we swap the value. The last node always swap the value with the 0. So that's the index value and the 0 index value, they will swap. So after they swap, actually this one is the target. The parent index actually is in the with the wrong value. So that's why we need to push them down. So that's why you see you have another loop. So this loop is what? We need to make sure this value will be in the right location. So that's why we will see here is the parent index. So we can calculate the left children and the right children index. So see you if your so then we will see if the left children greater than the index, we finish. Or the right children index greater than the index. Actually, that's mean you only have one children. So did you see here? This one, we are using the index as the boundary. But here, this one, from here to here, actually, did you remember that's our pop operation we talked about last week, right? So whenever you have pop, you pop the greatest value. So we're using the last node value to the top. So then we just need to continue to have the top node demote to the right location. So that's why usually we have our parents index value, the left children index value, and the right index value. We see which one is the greatest one, we will promote them. So that's why from here, this part, I don't go detail. Because you can see this one, we already do that before. That's our pop operation in the priority queue. So if you only have one children, that's right children. If the right children value is greater than the parent's value, so then we swap. Otherwise, if you have both children, but the left children value is greater than the right children value and the parent value, so we swap the left children. Okay, so then that is the pop operation. So that's why after you finish this, our outer loop is the for loop. That's N. So the inner loop, because that's the pop operation, our level only log N. So that's why after you have another N log N runtime for the DQ, at the end, your result will be in the sorted order. Yeah, so here actually I didn't give you the final answer. So actually they will have one iteration, couple different iteration. You need to try by yourself. So then at the end they will get 1, 3, 4, 6, 7, 8, 11, 12. So that's our HeapSort. You were just using your concept from last week priority queue to do your in queue like the push, DQ like the pop. So then you will have your array sorted.